All right, so at the beginning of second period, we've been working on number 58. I had everybody kind of go through and do A, B, and C. So those of you watching at home, I highly recommend that you pause the video and see if you can do question number 58, okay, on your own. Because this is just a kind of good common ion type problem. So when I look at this though, I had the KSP is given. We found this in the back of the book. KSP, well, what is the LaF3? What's it going to dissociate into? La3 plus. Okay, and I know that because it's -1, so it's -3 plus 3. And then what? Okay, but how many? 3 F minuses. All right, so my equilibrium expression, KSP, is going to equal 2.0 times 10 to the -19. Now look how small that number is. So do we expect very much of this to be dissolved? No. Okay? It's going to equal x times what? 3x cubed. Oops. And make sure we do the cubed on the outside, because we need to cube the 3 as well as the x. Okay? So that's going to be 27x to the 4th. So we got to make sure we know on our calculator how to do all those powers. I'm assuming in math you guys do that all the time. Okay? So x, in this case, is going to equal my La3 plus, which is going to equal my LaF3, which is really, this is the one we're worried about. That's the one we want. That's what the question's asking for. And what does that equal? We're dividing by 27, taking the 4th root. 9.3 times 2 to the -6. -6? Okay? Again, that's not very concentrated at all. Very little is coming into solution. Do I have somebody agree with that number? Yeah, okay. I always have to make sure because 2 years ago, 3 years ago, I had a guy, I'm not going to say his name. He was great. He came to class prepared, energetic, enthusiastic, did the calculator on every problem for me. Every time it was wrong. I mean, he could not, so I always had to double check, you know, because he was just gung-ho, do it, you know, punching it in, and then it would always be the wrong number. So I always have to kind of double check, just make sure 2 or 3 agree that it's the right number. So this is the solubility in pure water. Okay? 9.3 times 10 to the -6. But now when I go and do this, it says in oh well, is this actually the answer? It's always important to go back and read the question, because what's it want? Grams, okay? So how do I take 9.3 times 10 to the -6 molar LaF3? How do I get that to grams per liter? By how much? 195.91 grams per 1 mole. And notice that molarity is always going to be moles per liter. So my moles cancel, and I'm left with grams per liter. So this is an important, and even if we need to be able to go to grams per 100 milliliters, which would be a tenth, you just divide it by a tenth. Okay? But what does that come out to?
1.8 times 10 to the -30, I think.
Yeah.
Okay? That's the actual answer. It's just taking molarity to grams. It's just the reverse of the one we did where they were giving us the concentration in terms of grams per 100 milliliters. We had to convert that to molarity. This is just going the other way. So now B. Now this time in B, we have a common ion. What's the common ion in B?
Fluorine.
The fluorine. Okay? Now Caitlin asked a great question. Do I multiply this, because of this 3F, do I multiply the 0.01 times 3? you shaking your head? No, why?
You just subtracted from the 3x.
Okay, subtract it?
Or add it, I mean.
Add it to the 3. Because you look at the source of the fluorine. The source of the fluorine is Kf. It's not Kf3. So the fluoride ion concentration coming from the common ion is 0.01. The fluoride ion concentration coming from the LaF3 is the 3x. So we're going to say then that 2.0 times 10 to the minus 19 is equal to x times 0.010 plus 3x cubed. Is everyone good with that? Yeah? Okay? Now we assume x is negligible. And the assumption is made when the concentration of the given, the common ion, is at least 10 to the 4th times greater than the K. It's way, this is 10 to the minus 2, this is 10 to the minus 19th, or 10 to the minus 17th different. So this assumption is going to be pretty valid. Okay? So that means that 0.010 plus 3x approximately equals 0.010, the two sig figs. So that just means we can ignore it. So it's going to be 2.0 times 10 to the minus 19 is equal to x times 0.010 cubed. X is going to equal my LaF3 concentration. It's also going to equal my La plus, but I'm more interested in the 3 plus. I mean in the LaF3. What does that come out to? 10 to the minus 6, so 2 times 10 to the minus 13. Okay, but again, it wants grams, so what will we have to do to this? How do we convert it to grams?
Molar mass.
So we just multiply by the 195.91 again, right? Is equal to 2.0 times 10 to the minus 13 times 195.91, and that equals
3.9 times 10 to the negative 11.
That's grams per liter. Notice the solubility went from 10 to the minus 3 to 10 to the minus 11. Adding a common ion always lowers the solubility. It's always going to be more soluble in pure water than it is in one with a common ion. Now, when we go to part C of this one, now 2.0 times 10 to the minus 19 is going to equal what? What's my common ion this time? The La, the lanthanum. So I'm going to say is equal to x plus 0.050 times 3x cubed. Right? So again, we assume x is negligible, so it's going to be 2.0 times 10 to the minus 19 is equal to x, pardon me, it's equal to 0.050 times 27x to the third. Okay, so you could either multiply this out or you can divide by 0.05 and then divide by 27. Solve for x, which again is equal to my La3 plus, which is equal to my LaF3, and that equals what?
I got 5.3 times 10 to the negative 7.
5.3 times 10 to the minus 7. Do I agree on that number? I saw one head shake. I see several that are just saying, I gave up on the last one. Okay, now again, that's not my answer. So 5.3 times 10 to the minus 7th moles per liter LaF3 times the 195.91 grams per mole. That equals
1.0 times 10 to the minus 4.
Okay, now notice, this one took it to minus 11, that one only took it to the minus 4. Why?
Because the fluorine has like a bigger impact on it.
Fluorine has, we're cubing this, okay? So this, you know, when you have adding more fluoride, it's gonna have a much greater effect on the overall amount because you're gonna be cubing that number. So that makes the lanthanum even smaller that can come into solution. Okay? Did y'all get all that one right? I'm seeing a lot of mental fatigue going on right now. Okay? Y'all are too quiet. We good? Okay, so I'm already shaking a hand, maybe iffy. What part is a little cloudy still?
Well, I'm like setting it up right and everything, but like I'm just a little off. So like I'm making like simple mistakes. So like for instance, like on C,
Okay?
like the 3x to the third, like I just forgot to do like 27.
And this you did 3x cubed instead of 27x cubed?
Yeah, that's what I did.
Yeah, that's a common mistake. And that's why I say make sure that you put the cube on the outside of a parenthesis. So otherwise, if you just cube the x without putting the parenthesis, you're gonna think it's 3x cubed. Good thought. Anything else? Come on, y'all. Get fired up. It's Monday. You're refreshed. You had a great weekend. Yes, ma'am.
So if the x is like negligible, then why do we need to put it
Well, just because it's just showing that, okay, this, I'm just showing that the concentration of the lanthanum is gonna be from both sources. Okay, that it's gonna be this, and this is what was put in initially, and then this is what's gonna come from the LaF3. But that, I mean, it also lets us know what X is representing on that. Okay, so whether or not, if you never put it in there, if you just made the mental assumption and just put that number, I'm trying to think of what they said on the grading on that, whether or not, how acceptable that was.
This is a random question, but will naming be on the AP?
No.
No. Okay.
I've never seen, I mean, they'll use it, and the more comfortable you are with the names, as far as when they're using names, big names, and the problems, I think it helps, but I've never seen a question, what is the name of, anything like that. All right, those are the three main types. Let's do one more today. And then I'm gonna spend 20 minutes tomorrow on the fifth and final type, which is gonna be a bonus, and I'm not gonna go into it much more than that. But we actually do have a second lab on this one.
Yeah.
So, we'll see. All right. The fourth one. Will a precipitate form when two solutions are mixed? Will a precipitate form when two solutions are mixed? Still on page 770. Looking at question number 69. I'm erasing. Y'all just need to be breathing, stretching your neck, getting fired up, refocusing.
Stretch.
Now, will a precipitate form? That means that when I calculate Q, I'm going to compare Q with KSP. If Q, so you're going to calculate Q. And compare to the given KSP. If Q is greater than KSP, a precipitate will form. I don't think I need to write the converse. Now, obviously, then if Q is less than KSP, what does that mean?
Won't form.
No precipitate will form. Okay, so will a precipitate form is a Q problem.
Where does equal to
If it's equal to, then it still will not dissolve, it will not form a precipitate. Because KSP is the maximum amount that can be in solution together, the two ions. All right? So we're going to calculate Q. Will calcium hydroxide precipitate from a, we're going to do B. See, this is chapter 17, chapter 16 talks all about pH. So we don't know how to do that one yet. Okay, but we can do B. Will silver sulfate precipitate when 100 milliliters of 0.05 molar is mixed with 10 milliliters of 5 times 10 to the minus 2 molar sodium sulfate? Okay, so I am going to get silver nitrate combining with sodium sulfate, and it's going to make silver sulfate plus 2 sodium nitrates, and all nitrates are aqueous, so I need to have a 2 right here. Okay, so that's my mixture. Now, the KSP for silver sulfate is what, Advon?
1.5 times 10 to the negative 5.
Okay, so that's my silver sulfate, which means that my Ag plus squared times SO4 2 minus cannot exceed this number. Now again, I know that it's squared because it's Ag2SO4. Okay, so I'm always interested, when I'm mixing a solution together, I'm interested in the precipitate. Will a precipitate form? So I do the equilibrium, the KSP, for the solid. Just like we've done all along. But now what I have to say is the silver is all coming from the silver nitrate. The sulfate is all coming from this. So I have to find out, once they're mixed together, is the concentration of silver squared times the concentration of sulfate, is that going to exceed this given KSP? So I have to find Q, meaning Q is exactly the same as KSP, and then just compare it to my given KSP. Now, what makes this problem even trickier is when you mix the 100 milliliters of this with 10 milliliters of that, we're diluting it. Okay? So, I have to get my silver concentration. The silver concentration, and remember dilution, how do I do this dilution problem?
NC, BC.
Okay? MCBC equals MDVD, right? We just did that with the kinetics lab. We just did a whole slew of them. But we can just say that when we do that, MCBC is equal to MDVD. We want the molarity of the dilute, so we're just going to go over here, volume of the dilute. Well, what's the volume of my dilute going to be? 110. The volume of the concentrate is going to be 100, so it's just going to be 100 divided by 110 times my initial concentration of 0.05. So what, well, let's get a number for that.
Point 045.
So that's the, once I mix the two solutions, that's the concentration of my silver ion in the solution. Do the same thing for sulfate, except it's going to be what over what? 10 over 110 times my sodium sulfate. And again, it's 1 to 1. Now, if I was looking at sodium here, I'd have to multiply this by 2 because I'm going to get 2 sodiums. But I'm only interested in the sulfate, and it's a 1 to 1. So, but now I don't know why they did that way. What's 5.0 times 10 to the minus 2 is exactly the same thing as 0.05.
0.0045.
Okay, so these are my diluted concentrations. The diluted concentration, in other words, after I mix them together, this is the actual concentration they're going to be in the solution. Just like when we did the kinetics and we mixed everything together, by the time they all reacted, they weren't the same as we put in initially. We had to find that diluted concentration because that's what they actually reacted at. The KSP says that this concentration times this concentration, the maximum that can be in the solution can't exceed this number. So I'm going to calculate QSP is going to equal silver 0.045 squared times my sulfate 0.0045, and that QSP is going to equal
9.11 times 10 to the negative 6.
Okay, so is that greater than or less than the given K? Less. Q is less than K, therefore what does that mean? No precipitate will form. Okay, so we would think, okay, I put these two together, we're going to get a precipitate, but if we put in just super dilute solutions and only a little bit of that second one, then there's not enough present to actually cause a precipitate to form. And notice this KSP, relatively speaking, is a fairly big number. Most of them are around 10 to the minus 10, 10 to the minus 11, 10 to the minus 18, 19. 10 to the minus 5 means that it's not soluble, but it's kind of soluble still. So the bigger this KSP value, the more that actually does dissolve. Okay? So, when you're doing these problems, these are a little bit trickier. Number one, you have to calculate the diluted concentration. Always put with the initial amount over the final amount. It's a super easy. This is how you do any dilution. It's always the initial amount divided by the sum of what you're mixing times the initial concentration. And again, that's just like we did in the kinetics lab, it's just like we did at the first semester when we did solutions. Okay? So find the diluted concentrations, put them in, solve for Q, compare the value to KSP. All right, 3 steps. So, let's finish the day. You guys doing this one, number 70. And do B again. A is the pH again. We'll learn how to do those when we do acids and bases. Just do B. Well, I guess the reality is there's a typo here. That's supposed to be NO3. You won't change anything, but except in the reaction, you're asking the precipitate if it's AgNO3 is mixed with NaIO3. That's going to make your AgIO3 precipitate. And then if you can't read this, this is 3.1 times 10 to the minus 8. That says 10 to the minus 8. 3.1 times 10 to the minus 8 for KSP. Follow the pattern of that previous problem. KSP student, right there. 3.1 times 10 to the minus 17. Two minutes. See if we can get done in 2 minutes. All right, just for the sake of time, so we can at least get some closure on this one. How do I find my silver concentration? What over what times what?
20 over 30 times 0.01.
And that's gonna be 2/3 of 0.01, so it's 0.00667 or 0.0067. Okay, what about the iodate?
10 over 30 times 0.015.
That's 1/3 of 15, so that's gonna equal 0.005 molar IO3 minus. Okay, so step 1, get the diluted concentrations. Step 2, calculate Q, plug into my Q expression. QSP is simply going to be Ag plus times the IO3 minus, it's 1-to-1. Okay, got it right out the equation, but it's Ag IO3 goes to Ag plus IO3 minus. So that's my equilibrium expression. So I'm just going to plug in 0.0067 times 0.005, and that equals what?
3.35 times 10 to the negative fifth.
Times 10 to the minus fifth. So Q is greater than KSP, therefore a precipitate will form. Okay? So, that's 4 of our 5 types of KSP problems. So together, we're just going to have our equilibrium, straight up equilibrium, where we're going to calculate K, Q, Kc, Kp, given concentration units, and those concentration units are given in one of 3 ways. Or we're going to go the reverse, we're going to be given K, and we're having to calculate concentration. Then we come in and do KSP problems, where we find the molar solubility given KSP, or we find KSP given molar solubility. What's the molar solubility with a common ion? And now, will a precipitate form? And again, will a precipitate form is always an indication that's a Q problem. Again, Q is not mentioned anywhere in the problem, but will a precipitate form has to be your mental clue that you're going to solve for Q. Tomorrow we'll come in and do when you mix two, you gotta get two precipitates forming. The question is which one will precipitate first, and that's actually what our second lab is based upon, is selected separation by precipitation, and it's based upon which one precipitates first. And we'll do that lab next week, and that's a good one. It's a titration, so it's a good learning how to do that, but it's also an expensive one because we're going to use silver nitrate. Your lab fees at work again. Okay. All right. So it was a heavy day today, but that's a good Monday. The rest of the week shouldn't be quite as heavy.